Hi everyone, I'm Takahiro Haruyama. Today I talk about my internet-wide malware C2 scanning research focusing on APT malware. I'm a senior threat researcher with VMware Threat Analysis Unit, formerly Carbon Black. I did several researches in the past, such as firmware acquisition, MITM attack, defeating compiler level obfuscations, Cobalt Strike team server scanning, and so on. First of all, please take a look at this virus total result against one IP address. Antivirus engines detected it as harmless, zero detection. But I'm sure it's malicious. In fact, this IP is a WinNTI version 4 C2 server with TLS protocol. The C2 server has been active at least since February and probably even now. Why can I conclude that? Because since 2019, I've built a system discovering active malware C2 servers on the internet by protocol emulation. Then used this intelligence to detect and stop threats in almost real time. As I show in this example, IP reputation is not effective for catching fresh malware C2 servers, especially when APT actors limit their malware deployment to specific targets. In this presentation, I will explain how to emulate the C2 protocols of two long-term APT malware, WinNTI version 4 and ShadowPad. This is today's overview. First, I summarize the target malware in this table. Both are utilized by PRC-linked cyber espionage threat actors and support multiple C2 protocols. The big difference is the prevalence. There has been minimal reporting on WinNTI, while there are a lot of publications regarding ShadowPad. I will explain details, including the unique feature in each section. First, I explain the WinNTI version 4 C2 scanning. WinNTI is malware seen in many large-scale attacks and has been attributed to APT41 at the list. In 2013, WinNTI was first reported by Kaspersky. And in 2015, Novetta analyzed the startup sequence and C2 protocol of version 3. The WinNTI version 3 components are separated into three components: dropper, service, and worker. Dropper decrypts and saves service and worker. Then service runs worker. That is a payload. In 2016, I observed the version 3 startup sequence changed. Macnica Networks first described the new variants at JSAC, Japan Security Analyst Conference. To differentiate from other previous versions, I refer to the variants as version 4. The version 4 is more carefully implemented to make the worker code acquisition harder. That's why there is very limited public information about this version. In 2018, I identified a new worker component whose C2 protocol was completely different from the existing version 3. So I analyzed the new version 4 C2 protocol. The version 4 worker component supports 5 C2 protocols. Basically, the same customized packet is handled in every protocol, but there are minor differences and additional structures. TLS and HTTPS are encrypted versions of TCP and HTTP. As a unique point, this malware has a server mode accepting incoming packets. It behaves like a C2 server. This behavior was helpful to verify the correctness of the protocol format and encryption for the C2 scanner development. The customized packet is separated into header and payload. Both are encrypted, except for the temp key seed value in the header. The signature and payload length values are checked after the decryption on the receiver side. The initial handshake packet payload contains payload type, GUID, packet sequence number, and so on. Actually, the packet encryption algorithm is still unknown, so I emulated using IDAP core. There are two kinds of keys. One is different, dynamically generated key from the temp key seed value. This code shows the key generation. The other is a portion of the Sherman hash value over hard-coded string. In the TCP and UDP protocols, the customized packet data is simply sent. On the other hand, in HTTP protocol, the packet is sent through a post method with several headers, and the cookie header value contains its packet size. The cookie header value is a string made up of 5D word hex values in little endian. By using this calculation, the previous example value is decoded as 34 in hex. Prior to the post request, an initial GET request will be made. In the GET request, all values except the cookie are randomly generated. So the decoded size value is 0. I'm not sure about the purpose, but this behavior can be utilized for the C2 scanning. After the initial handshake, the packet payload contains the command ID and dispatcher ID in the nested structure to control the infected host. Most C2 commands are related to plugin management, like version 3. The detailed commands will be compared with another malware called Spider later. For the WinATI version 4 C2 scanning, I implemented 2 Python scripts. It's unrealistic to scan full range of IPs on the internet with Python scripts. So I first use ZMap to generate input port scan data. Next, the standalone Python script handles 2 kinds of packets. In HTTP protocol, the script sends a GET request, then decodes and validates cookie value of the response. In other protocols, the script sends a fixed customized packet, then gets suspicious responses with the same size and different key for excluding honeypots. After that, the IDPython app call script decrypts responses customized packet and validates the values in the header. By the way, I explained WinNTI version 4 supports the server mode. So how can we differentiate server mode infections and C2 servers? At least in TCP, TLS, and UDP protocols, we can identify the difference by checking the GUID and packet sequence number values in the decrypted payload. Specifically, server mode infections send back the same GUID value as client, and the packet sequence number is incremented. On the other hand, C2 servers return a null GUID value, and the packet sequence number is reset. So we can differentiate them. I show the scanning result first, population by protocol. I've scanned WinNTI version for C2 servers since December 2019. And so far, I've identified 55 servers in total. All were likely C2 servers because in TCP, TLS, and UDP protocols, I could validate by payload values that I explained in the previous slide. And in HTTP protocol, the scanners just decodes and validates the cookie value, but the discovered IPs were hosted by VPS providers, which were overlapped with other protocol servers. So that's why I concluded all were likely C2 servers. I guess the server mode infection samples use high ports for binding. This graph shows a change in number of active WinNTI version for C2 servers per month. I disclosed the C2 IOCs twice, February 2020 and November last year. I think that's why the number in November sharply dropped. Even now, around 10 C2 servers are still active. As far as I know, there are only 2 public reports related to WinNTI version 4 C2 servers. Both were published last year, about 2 years after I disclosed. I will keep tracking the C2 servers on the internet as long as the malware is used. The next scanner example is ShadowPad. ShadowPad is a modular malware platform privately shared with multiple PLC-linked threat actors since 2015. According to Sentinel-1, this is the successor of PlugX. ShadowPad supports 6 C2 protocols, but in this research, I focus on TCP, HTTP, and UDP protocols because SSL and DNS are not likely utilized by the recent samples, as far as I know. The C2 protocol format and encoding algorithm are different between TCP and HTTP UDP protocols. For example, the key for the packet encoding is included in the header in both protocols, but the key size is different. And the header size also different. And randomly sized data will be appended as the payload to the initial handshake packet. The size is random, but the maximum size is different for each protocol. Besides, the immediate values used by the encoding algorithms are different per variant, probably per ShadowPad builder version. So I analyzed the 3 variants collected in August last year. Variant 1, also known as ScatterB, reported by Positive Technologies. Variant 2, reported by ESET. Variant 3 was hunted from VirusTotal at that time, but a few months ago, Positive Technologies also reported it. The TCP protocol header format has been the same since 2015. The session key is randomly generated, then used for encoding both the header and payload. The next field contains plugin ID and command ID. The IDs are different per variant. My C2 scanner utilizes the compressed and original payload size information for the format validation. The TCP protocol packet encoding is like this in Python. Among the shadow path variants that I analyzed, only variant 1 had the TCP plugin for C2 protocol. So another variant may use different immediate value for the encoding. And after the initial handshake, shadow path executes C2 commands specified by the C2 server. For the individual command IDs and payload formats, please refer to the Dr. Webb white paper. The sample analyzed in the paper is older than variant 1, but the formats should be similar. In HTTP and UDP protocols, the header and payload are sent as raw data in UDP or through a post method in HTTP. The header format also contains session key for packet encoding, but the key size is different. And the next field is constant value. I call it type. And others are session IDs. The session source ID sent by the client will be set in the session destination ID on the server side. So we can utilize these red-colored field values for the format validation. In HTTP and UDP protocols, the immediate values in the packet decoding code are different per variant, but the algorithm is identical. After the initial handshake, the payload will contain the same data structure as the TCP customized packet, and the type field in the header will be incremented. Before the scanner implementation, the target protocols and ports were decided based on the recent samples configuration values. I had to implement the scanner per variant due to the difference of immediate values used in the packet encoding. Like WinATI version 4 C2 scanning, first I create a list of hosts open at targeted ports using ZMap. Next, the standalone Python script sends the shadow path formatted packets to all IPs on the list, then decodes the response packet and validates the decoded values. In TCP protocol, payload size information in HTTP and UDP protocols, type and session ID will be checked. By the way, during this research, I found one shadow path sample including exactly the same hostname and port except protocol. That hinted shadow path sheets can accept multiple protocol requests at a single port. So I tested my guess by scanning one active shadow path C2 server. As a result, the C2 could accept both protocols at the same port. This is the reason why I just scanned the HTTP protocol, not both. The same behavior may be seen in other protocol combinations like TCP and SSL or UDP and DNS, but I've not researched yet. This graph is a population by shadow path variant. I've scanned shadow path C2 servers since September last year. And so far, I've identified 83 C2 servers in total. During the tracking period, variant 1 had become more active. And this is a change in number of active shadow path C2 servers per month. The sharp drop in February is just a system issue. Currently, around 10 C2 servers are active. The scanner may have missed new variants lately because shadow path changes the immediate values used in the packet encoding algorithm per variant. So I will keep tracking, keep improving the scanner while hunting new samples. As shadow path is more prevalent than WinNTI version 4, I could identify 3 samples on VirusTotal communicating with the discovered shadow path C2 IPs. All malware are utilized by PRC-linked cyber-espionage threat actors. Spider is used by APT41. Reverse window is used by Royu, named by CB22. And all C2 servers were discovered by the TCP443 variant 1 scanner. And except the Spider case, the C2 servers accepted multiple protocols and ports at the same time. And in all cases, the C2 scanning system caught the C2 servers prior to the sample submissions. This is a big advantage by the C2 scanning research. By the way, Spider contains a code handling the same C2 command data structure as WinNTI version 4 worker. It has 37% code similarity. So I got interested and analyzed the command IDs of both malware. The C2 command is decided by a combination of 2 constant values. In the Dr. Ives Spider report, they call tag and ID. And in my analysis, I call command ID and dispatcher ID. They have almost the same functions regarding the plugin management. But the dispatcher IDs are different, and no command for sending connection information in WinNTI worker. This table shows the comparison between Spider and WinNTI version 4 worker. The WinNTI worker supports multiple C2 protocols and server mode. It also makes the payload acquisition harder than Spider. So I guess Spider is the lightweight version of WinNTI worker component. Let's get back to talking about the discovered shadow path C2 IPs. The discovery of a shadow path C2 IP triggered an incident response. The APT attack had bypassed many methods of endpoint detections, but it was alerted because of the pre-identified C2 IP. In this case, the C2 scanning technique worked as a proactive threat detection method. In this section, I'd like to share my findings for internet-wide C2 scanning, not limited to WinAPI and ShadowPad. I generate initial port scan data for the C2 scanning Python scripts using ZMap, not purchasing the third-party data service such as Shodan, Census, Rapid7, and so on. Because for UDP-based protocols, we must scan hosts with the customized protocol formats, or the C2 servers won't answer. The commercial services normally don't provide the option. Additionally, the commercial services don't scan minor ports actively. This table is the result of the number of IPs open at minor ports in last November. If the ports are not targeted, Shodan and Census return the extremely small data. So by choosing the minor ports, threat actors can avoid detections by Shodan and Census easily. That's why I generate input port scan data on my own. Another consideration is anonymization. Scanning operations are sometimes forced to be terminated by ISPs and VPS providers due to abuse reports. In order to sustain the research, the source address should be anonymized. There are two anonymization methods using Tor and commercial VPN service. Tor is free, but only supports TCP-based protocols and has a risk of being blocked because Tor exit relay list is published. On the other hand, commercial VPN service is non-free, but supports both TCP and UDP-based protocols. That's why I utilize one of commercial VPN services for anonymization. By the way, when we use ZMap with non-Ethernet interfaces, ZMap will cause a segmentation fault, and this bug has not been patched yet. So I recommend to patch using the code explained on the issue page. From here, I introduce anti-scanning techniques that I observed in the wild. The first case is Cobalt Strike. I've scanned Cobalt Strike team servers since February 2020 by downloading shellcode with an encoded beacon based on the Stager protocol. I observed some trivial but effective anti-scanning techniques. For example, as fake HTTP header, content encoding gzip is appended, but the content is not compressed. The content length size is more than the actual size to cause a connection reset error. Both headers will abort normal HTTP requests. Actually, I'm not fully confident, but some team servers provided the shellcode only when scanning through VPN. So I guess they blocked clients using Tor. Other than that, as anti-decoding methods, junk shellcode instructions, and randomized single byte extra key were observed. Basically, the key is fixed, but different keys were used in the wild. In a different malware case, different anti-scanning technique is used. I implemented the RUOU's reverse window C2 scanner in March last year. I think this actor is very nervous about C2 discovery because the C2 port numbers were minor and not scanned by commercial services usually. And the protocol format has been updated frequently. At least I implemented 3 different formats. Additionally, the initial handshake requires RSA public key and password embedded in the configuration data. I finally implemented several scanner versions for the malware, but the number of the discovered C2 servers were very limited. So this C2 scanning was not cost effective. I'm a researcher. My mission is a research publication. But I'm still not sure if I should publish or share this type of research because of the pros and cons. I'd like to share the pros and cons obtained from the past Cobalt Strike C2 scanning research publication. One of the good things by the publication is I could help to stop Microsoft Azure domain fronting. I identified multiple Azure-fronted Cobalt Strike team servers with cracked and leaked customer IDs. That means they were likely to be managed by criminals, not red teamers. So I provided the data with a person at Microsoft. Then 2 months later, Microsoft decided to stop and prevent domain fronting within Azure. Since then, the new Azure-fronted cases have decreased. Another good thing is I supported stopping an ongoing attack campaign. I've identified potential victims based on manual proxy settings of the Cobalt Strike beacon configuration data. And in August last year, I found one server had a cracked and leaked customer ID, and it was active at that time. So this was a real ongoing attack. I contacted the victim, and as a result, they blocked the campaign. On the other hand, there were some bad things since the publication, because the developer and threat actors also watched it. For example, I disclosed the DNS protocol details at the JSAC for the first time. Then 2 months later, the developer added new C2 profile settings, mainly focusing on DNS, to change the behavior flexibly. I think this was not due to only me, but Cobalt Strike threat actors have started to disable the Stager protocol. For example, APT41. The ratio of the Stager disabled team servers was 20 to 40% last year, now around 50% or more. They also have seemed to start to use redirectors because the number of discovered servers decreased. It makes the scanning harder. The cat and mouse game still continues. I wrap up my presentation. By emulating the C2 protocols, then scanning the internet, I've discovered over 140 WinATI version 4 and ShadowPath C2 servers. At the end of this month, last month, 65% of the IOCs have zero detection on VirusTotal. And around 10 C2 servers are always active in both malware. I think there is a little possibility of false positives because the C2 protocol formats and encoding are fairly unique. I believe the C2 scanning can become a game changer as one of the most proactive threat detection approaches. For this research, I appreciate two external researchers, Tadashi Kobayashi from Internet Initiative Japan. His advice regarding the scalable scanner implementation and troubleshooting was helpful. Leon Chan from Team T5, he shared his knowledge to gain a more complete picture of the shadow path variants. Thank you so much. And last but not least, I appreciate my manager, Brian Baskin, for his patient management as always. This is a sample hash. And the discovered C2 IOCs are published here. That's it. And if I have time, I'd like to demonstrate the C2 scanner. That's it.
どうもありがとうございました。
Thank you very much. Now we would like to go to the Q&A session. Due to time constraints, we would like to receive only one question. And if you have any question, please raise your hand.
よろしいでしょうか。
No question? Maybe not?
C2 scanner.
よろしいですか。はい、それでは、本講演これにて終了させて。
May I run the demonstration? I'm so sorry. Yes, please go ahead.
Just a moment. Can you see the screen? First, I demonstrate the WinATI HTTPS scanner. I hope they are active now. The scanner sends a GET request, then decodes the cookie header value of the response. And if the decoded size information is 0, they must be the WinATI C2 servers. So we can say they are active now. Next, I demonstrate the shadow path TCP scanner. The shadow path TCP scanner sends a TCP customizer packet, then decodes the response data. The response data look to be random, but after decoding, the data is always matched. So we can say these shadow path C2 servers are in operation now. That's it.